So I'm going to talk to you guys all today about the verification of a distributed system. And what we're going to focus on in this talk is, less about formal methods, although we'll talk about them briefly, but more about what you can take back in your day-to-day jobs to help build more resilient and reliable systems and increase your confidence that the system is doing the right thing. So I am Caitie McCaffrey. I am a distributed systems engineer. I work at Twitter, and I've been sort of all over the place in platform and developer tools. Prior to that, in a previous life, I worked in the games industry on titles like Gears of War and Halo. This is where you can find me on the internet. My DMs are open on Twitter, so if you have a question or want to think of something afterwards, feel free to hit me up on that. Okay, so let's just dive in and get started. So when I talk about increasing the confidence of that our system is doing the right thing, what we're really talking about is exploring the state space of all inputs into our computer program. So if you just visualize this circle as all inputs that are potentially into our system, how do we start exploring that state space and then verifying that certain combinations of inputs are doing the thing that we think they are? I also wrote this article in the Communications of the ACM, and then was also published in ACMQ, called The Verification of a Distributed System. That's sort of like the more formal, less fun version. This is the fun talk version, where I get to tell you more ridiculous stories and anecdotes, because you kind of have to keep your stuff buttoned up for the ACM. But this is online if you want to read it afterwards as well. Okay, so Leslie Lamport once famously said, a distributed system is one in which the failure of a computer you didn't even know existed could render your own computer unusable. So I guess back in the day when we were originally exploring the idea of distributed systems, this was okay, but it's totally not tolerable now to say, hey, some computer on the internet went down, sorry, you can't tweet, or sorry, you can't watch Netflix, or whatever your business of choice is, sorry, like this thing is not available. So we have to figure out how to make our systems more robust. And we're sort of all building distributed systems, so when I talk about this should be applicable to everyone, because it could be something simple like a client and a stateless service and a database, which is your canonical source of truth. This is a distributed system. It could be something like Twitter services, where we have all of our microservices that talk to each other and form these sort of like Death Star architectures. Or it could be something that you've inherited and people duct taped a bunch of things together, but you still have to maintain it because it serves some business function. And so how do we verify these systems? This talk should help us address all of these questions. So we'll start with a quick overview of formal verification if you haven't seen it. I'm trying to humanize it in this talk a little bit. It's really not as scary as I think a lot of people make it out to be. And then we'll spend the bulk of the time on testing in the wild and a lot of different techniques and research about how we increase our confidence in system correctness. And then I'll talk a little bit about research, because I always love doing tech transfer between academia and industry, and sort of providing you a new hope and maybe where I think we're going in the future. There will be a lot of information in this talk. I will tweet out a link to, this is on my GitHub account, there's a references section that has links to like literally every paper and thing referenced in here, or if you want to dive deeper, it'll all be there. I'll tweet that out and it'll be on a bigger slide at the end, so don't worry about that. Okay, so formal verification. So formal verification is an academic term, and we're sort of using math and propositional logic usually to say that a system is provably correct. So once we've done a formal verification of a system, we know that it's provably correct. It's mathematically correct, like there are no bugs in the systems. That's sort of the gold standard. This is typically done using a formal specification language. Either like TLA plus is one that's super familiar, or super famous, or COC is another one. And so basically, what it's doing with formal verification is you have all of the inputs, and we're exploring all of them with formal verification so that we can say that the system is provably correct, because we've literally analyzed every single input. And the way it's doing this with a formal specification language is you're sort of writing a proof, and I'll show you an example of that in just a second. And then we're either using a proof assistant, so like actually proving it using math that it's correct, or we're using a model checker, and all a model checker does is it explores all of the state space of all inputs into your system. This obviously takes a long time depending on how complex your system is. But then once the model checker runs and has exhaustively explored the state space, you can say, we're done. Everything is correct if it passes. So this is an example of what a formal specification looks like from TLA+. If you're super interested in this, Leslie Lamport actually has a book online called Specifying Systems that's for free, and you can just go read it. But this is how you would write a TLA+ specification for a hour clock, so a clock that goes from 1 to 12 and then like back again, because we're not on European time. So this sort of looks like code. It's just propositional logic. You write this, and then you would use a proof assistant or a model checker. But what we're doing is we're saying we have this variable hour. It extends natural numbers. So, and then basically hour can go from 1 to 12. Those are the valid ranges it can be in. So 1, 2, 3, all the way up to 12 in the natural number range. And then we're defining what the transition is like. So if hour is 12, or not 12, then do hour plus 1, else set it to 1. And then we're adding this concept of time. And so if you ran this, you could have a provably correct hour clock that only went from 1 to 12 and would never somehow set itself to some other number and would increase, in the correct order. So that is all a formal specification looks like. And the reason I talk about it here is it actually has found its way into industry. Amazon used formal specifications, and they published a white paper on it in 2014. And what they did is they used formal methods to verify some of their Amazon web servers that they have. So this is pretty cool. They basically went through, if you read this, they verified S3, so one of their core storage layers, and 10 other core pieces of infrastructure. They found 2 serious bugs, and then they increased their confidence to make optimizations. So finding 2 serious bugs doesn't really seem like maybe that was a lot of effort, it took a ton of time. But what they talk about in this technical report is that the bugs they found would have never been found otherwise. They would have only ever been found in production when a catastrophic failure had happened. So that's pretty valuable because they've just basically prevented 2 incidents from potentially happening. The other big win they found is that it increased their confidence to make these really aggressive performance optimizations because they still had a proof to say that this was correct. So that was really valuable because the developers weren't afraid to go and try these performance optimizations because they still had something that said, hey, this system is still provably correct. You're not going to introduce some bug that's going to cause data loss or something else. And why I think Amazon invested the time, and they talk about how they were going to continue to invest the time doing this in later bigger infrastructure projects, is because this is how they make money, right? They're selling you something to deal with databases and reliability and web services, and so it's very core to their business model to prove that it's correct. And I also think even if you don't ever write a formal specification for a real application, I think learning about it and thinking about it is really great. Because it forces you to think in a very rigorous way. And so Leslie Lamport has this quote where he says, it's a good idea to understand a system before building it, that's why we have design docs and things, but it's also a good idea to write a specification before implementing it because it makes you think so rigorously about the system that you're implementing, all the edge cases and failure cases, that you're more likely to just sort of find bugs just by thinking through the problem. And the Amazon paper also reinforces this idea. They said a lot of the bugs were found just by writing the system without even having to run the model checker or the execution piece. The other big complaint you'll sort of hear about formal methods is that they deal with models of systems, not systems themselves. So if you write something in TLA+, that's great, and it's provably correct, but now you have to go implement it in your language of choice, like, say, Java. So that kind of sucks, because now you still have to go and turn the specification into code, and obviously there can be bugs caused through lack of or things are lost in translation, or people just make mistakes, or whatever. So you still have to sort of test that system as well. The other specification language, Coq, actually will generate code, but it can only generate a subset of OCaml because it's not, we can prove that things halt, and so therefore it's not a Turing-complete language. But what's super neat is you can actually do quite a few things with writing something in Coq and then generating the code. So at an academic conference called POPL, which is about programming languages, in 2016, there were 2 papers published. One is about formal verification, where they wrote the Raft consensus algorithm, and they wrote it in Coq, and they proved that it's correct, and then they generated the code and they ran it, and it worked. So that's kind of cool. And then another one, they actually wrote a key value store. This came out in 2016 as well. They wrote a key value store in Coq, so a provably correct key value store, and then they generated the OCaml, and you can actually run it on a real network and make requests, and it's a provably correct data store. Now, is it the most performant data store? No. But this is kind of hopeful that maybe we have some tools that can help us generate more correct systems for these really hard distributed systems problems. And it's also a new area of research to say, hey, if we can generate code that is useful from formal specifications, we can also find ways to optimize that code, right? That's all compilers do. So this is an extension of things that I hope we get to in the future. But we don't have this necessarily today. So let's go on to something maybe a little more practical about distributed systems testing in the wild, as I like to call it. Or we're going for like seems pretty legit and like ship it. So one of the basic ones that we'll go through is unit testing. And I think everyone sort of knows about this, but the reason I bring it up in this talk is I think it's incredibly powerful, and we'll go through some research about why it's that powerful, and like that's proved it's even super powerful in distributed systems. So just for clarity, when I define a unit test, I mean something that can be ran locally with your CI system. There's no environment, it just needs a CPU, useful for basic functionality and testing of error cases. Okay, so this is my favorite paper from 2014. It's called Simple Testing Can Prevent Most Critical Failures. So this is another nice partnership between academia and industry where a bunch of academics said, hey, we want to understand the distributed systems open source community better. And they went and they analyzed a bunch of 5 systems in the distributed system open source space. They analyzed Cassandra, HBase, HDFS, MapReduce, and Redis. So these were all open source with open source bug trackers. And they found, they basically took like 198 randomly sampled bugs from these systems. And then they took them in-house and they reproduced them and they figured out like what caused it, did some root cause analysis, and we're looking at ways of how can we help people better prevent these things from happening in the first place when they're originally writing the code or designing the system. One of the key findings they found is that 77% of production failures can be reproduced by a unit test. So this was pretty surprising to me. It's really cool too because it basically means that, it doesn't mean you have to be like omniscient and like maybe necessarily guess all of the unit tests you need to write up front, but what it does mean is when you find a really critical bug, you can most of the time, like 3/4 of the time, write a unit test and add this into your CI suite to prevent it from ever happening again. So that's really hopeful because it means you won't have these regressions. Like once you solve something, it'll just like stay fixed, which is nice. And then they also found that testing the error handling code could have prevented 58% of catastrophic failures. So a catastrophic failure is something where like live lock in a distributed system, data loss, things like that. So basically what they're saying here is that we need to spend more time as engineers testing our error handling cases. We're actually really good at testing the golden path, or like this is what is supposed to happen, right? Like when everything's going fine. What we're not so great at is we sort of, say, oh, it's hard to test error handling cases, and so we don't spend a ton of time on them, but that's where all the bugs in distributed systems lie, or the majority of them. The other 35% of catastrophic failures around error handling, so basically a lot of this is also just what I call dev laziness. So the error handling code is simply empty or contains a log statement, so I guess it's in the log, I guess that's okay. Error handlers abort the cluster on an overly general exception. So in Java, this is like when you say catch exception all and just like keep going, because it's kind of annoying to like catch each one, but like, right, this goes back to code cleanliness and maybe spending a little extra time there because it is valuable. My other favorite one is error handlers contain comments like fix me or to do, and then just like don't do anything, so it just swallows the error, and then your system keeps going. So that's problematic. So what we should take away from this, this piece of research is that we really need to test our error handling code, and we can use things like code coverage tools to help us do that. I use this with my teams, where we actually go and have code coverage that runs, and I'll go and sort of look on code reviews about what error handling cases did I miss before I submit a code review, and make sure I have tests that explicitly execute most of those, because that's where the bugs are probably going to be. Okay. We're going to have a brief interlude and a quick rant of Festo. I like typed languages. I actually I prefer writing in them way over untyped and dynamic languages, but types are not testing. So if you come to me and say, oh, well, I have a typed language, I don't need to write test cases, I'm probably going to get really mad at you. And so I sort of want to tell you this like story just to illustrate the point where I was working with a younger developer, and he really, really liked typed languages. And typed languages are super cool. So I was like, yes, they can help me do a lot of really great things. This is an active area of research, so they're going to help us do even more things in the future. But he was like, I don't really need to write test cases. He submitted this code review where he's like, I don't need to write test cases because the method signature prevents this bug from ever happening. And I'm like, okay. So I keep going through, and I'm reviewing his code. And I find an infinite recursion bug, I think. And so I'm like going through, and so I leave a nice comment. I'm like, hey, I think there's maybe an infinite recursion bug here. And he's like, oh my God, you're totally right. Like, and I'm like, maybe let's add a test case that at least proves that your code halts after like so many executions and doesn't blow up our stack and cause an outage because like the JVM got really sad. So, caution, types can help you. but they obviously don't encode all the semantics like this super dumb example does here, where the method is called add, and I'm actually multiplying them. A simple unit test case can help you go a long way. Also, TCP doesn't care at all about your type system, so like once you go over the wire into distributed systems, like all bets are off. Like the types are not going to help you there. So we basically have to go to our next topic, which is integration testing. So integration testing is basically the idea that we're just going to test the integration of all our models and verify combined functionality. This is super valuable because you're usually just testing a lot of boundaries between your organizations as well, because that's sort of how the work gets broken up and how things got specified. So when I was working on Halo 4 and we were rewriting the statistics service, we stood up the new one. We were all proud of it. We were like, we weren't in production yet, but we stood up the new one. We're all proud of it. We started integrating it with the day-to-day like game testing and play testing that went on. And I noticed this really weird thing where the game was sending us everyone's stats at the end of the game, which is a 15K blob, so it's pretty big and pretty expensive to process that, 3 times. And I'm like, why are you sending it to me 3 times? I 100% don't want it 3 times. I would like it once. When I tell you I finished processing it, then like don't send it to me again. And so this sparked like I think a 3-day like battle / like comedy of error thing going on between me and the main networking dev, where I'm like, look, like we're sending you an HTTP 200 back, and he's like, no, like you're sending us like a failure back. And so finally, I like went spelunking through the old code base to figure out what was happening, and I found that the old code base happened to put something in the payload of the response, which was done in all capital letters, exclamation point. And so I was like, wow, if that's it, I'm going to be really mad. But I put it in, and then the game stopped sending us the request back every single time. And I was like, cool, okay, so the spec was not following HTTP 200, and we did fix that in the original game. But this is sort of where things break down. Like the game engine and the old services were looking for the word done in all caps exclamation point to say like, hey, you processed it correctly. And this is not that weird of a story. If you work with a ton of different clients, like sometimes they don't support HTTP. The Xbox 360 didn't even have a formal HTTP library until, I don't even know, like 2011, and then we weren't allowed to use it because of memory constraints, because you don't get anything in games, you just, like, it's all graphics, gets all of the memory. But like, this was a thing, so we ended up fixing it, but like the integration testing prevented us from helped us catch this early and not cause additional load at launch that would have certainly taken down the system. The other super interesting thing, I think, that came from simple testing can prevent most critical failures is that they found that 3 nodes or less could reproduce 98% of failures in these distributed systems. Remember, they looked at HBase and Cassandra and HDFS and a couple other, and Redis, and one more that I'm forgetting off the top of my head. This changed my perspective dramatically. Because I was sort of under the impression that, like, yeah, there's no data like prod data, which is still true, but you also, like, in order to produce these catastrophic failures, you had to have these really robust staging environments to not just do the testing in production, and that's super expensive, right, to, like, stand up, you know, multiple 100-node clusters in staging and in production and have them running to do testing. This changed my perspective, because now all we have to have is a 3-node cluster. I can run a 3-node cluster on my laptop. So I can do really robust testing, do a ton of error handling and things like that. We can work these into integration tests. We can work these into different release cycles, because 3 nodes is very, very doable to test things on and will prevent a lot of failures. Another type of testing that I think is less well known but is super awesome is called property-based testing. So this is sort of borrowing ideas from the model checker space. So model checkers, remember, are this idea that we exhaustively list all the inputs, and then we sort of go through them in some order, and then once they all pass, we're like, cool, our code is good to go. The problem is it's super expensive and takes forever to run, and as you have these really large systems that you're running with CI and continuous deployment and microservices, like this becomes untenable. But what property-based testing does is it takes this idea of doing random inputs, and it'll run them for a certain amount, like you can specify I want to run 100 combinations, 1,000, whatever. And then it'll return you results that are incorrect. And it'll hopefully shrink, some of the better ones will actually shrink down even very large sets of inputs. Like if it took 1,000 inputs to get it to the bad behavior, it'll shrink it down to the ones that actually matter. So this is neat. This was invented by John Hughes. The original one is called Quick Check. It's written for Haskell and Erlang. So the idea here is you define a specification instead of a test case. I will show you what one looks like in Scala. Basically, it's code. It looks like writing a test case. It's not even as scary as formal specifications. And then you just sort of say, the tool will generate a bunch of inputs and then shrink the state space down, and then we'll send you a bug report. It'll say, like, hey, they all passed. So quick check is super great because they've found a ton of really, really interesting bugs in distributed systems like Reoc and Basho. Basho has a NoSQL database called Reoc, which they use quick check on heavily to model their eventually consistent data store and found a bunch of bugs. John Hughes went and ran quick check on Volvo cars and found a bunch of bugs in April of 2015. And then in February of 2016, he ran it and found some actually pretty big bugs inside of Dropbox. So this does take time, but once again, these are bugs that are difficult to find and often result in data loss or really bad things happening to your users, so that's what we want to prevent. The JVM has Scala check, so that obviously works with Scala and Java. It's super friendly, and then if you use any other language, there's like a whole page on Wikipedia that's linked in my references section. There's basically an implementation in almost any language you want to write in because people find this super useful. So here's a super simple Scala check example. The first one is basically just super dumb to show you the syntax. It's saying we want to make sure that the number we put in is always between 0 and 100. So I define a property which is for all small integer values, n must be bigger than or equal to 0 and less than or equal to 100. If I find a case based on this generator that only generates number from 0 to 100, then it'll blow up. So if you wanted this test to fail, you could do 0 to like 101 and it'll find it, or 0 to whatever. A more interesting example is the one below, where it is testing my implementation of a reverse on a list of strings. So Scala check will generate a bunch of different lists of strings of varying sizes, and it will put this into my function, and it'll do the reverse of the list should equal the list itself, right? So this is super nice because it'll catch a ton of edge cases, right? Just think of all the things where like, different sizes, different character sets, all that kind of stuff. So it'll hopefully find them if you run this for a while, if you have any bugs in your code. I find this super useful. I use property-based testing with one of my teams. And even just personally, it helps me think more rigorously through a problem, right? This is getting closer to the propositional logic of formal specifications, and so you'll find stuff just having to think through. Do you have a question? So the question was, why is property-based testing different than a unit test? So why it's different is because Scala check is a system that will run under the hood, and it'll actually generate like maybe 1,000 or 10,000 or however many you specify instances of a list to do the reverse of the reverse. A unit test, you would have to maybe you're already doing this. You can definitely do this on your own where you generate a list, then you run the same unit test 100 times if it's randomly generating a list. This is just a helper to do that, so it makes it a lot easier. Does that make sense? So these frameworks help you do this testing, and it literally, once you start doing this, it's about as much effort as writing a unit test, but you explore way more of the state space. So that gives you more confidence that it's doing the right thing. Okay, and then one of the other big ones that is different for distributed systems testing is you have to do fault injection testing. I believe this is super core. If you don't explicitly force your system to fail, it's unreasonable to have any confidence that it will operate correctly in failure modes. So this has become more popular. Netflix obviously has the Simian Army, which they've been doing for a long time. So they have Chaos Monkey, which will kill an instance. So that's the injection of a type A fault, which is a machine itself dies. There's Latency Monkey, which will inject latency into the network. So that's a different type of fault injection, adding some asynchrony to the network. And then Chaos Gorilla takes down an entire data center. So that's another type of fault injection test. And they've obviously built a lot of infrastructure and stuff around this to support it. Another really interesting version of fault injection testing is this tool called Jepsen. It's open source. Kyle Kingsbury wrote it, and actually now has a business where you can pay him to Jepsen your systems. He also writes this really great blog post where he'll basically take a distributed system, and then he'll run it through Jepsen. And what Jepsen does is it spins up local clusters on this really beefy machine he has, and then injects faults, creates network partitions on the machine so that certain instances of different nodes can't talk to each other. And then I'll sort of verify that the claims that were specified, either in their marketing documentation or whatever, are upheld. And so what Kyle started finding when he first started running this is that most of our distributed systems kind of look like this, and we pretend everything is fine. But the good news is since he started doing this, I think it's really increased the notion that we need to start A, testing our dependencies, and B, really like being a little skeptical about the claims of some of the open source software out there because it's hard to write these systems. And then he'll also, file bugs, and they'll be, a lot of times they get fixed. MongoDB is one where he's tested that a lot. It's added to a lot of fixes. He's found a bug in, Kafka that was pretty bad that got fixed. He's found all these bugs. So he has this great blog if you want to read them, and it also is a nice introduction to sort of like all the different consistency models and what's going on, and the open source ecosystem. So I just want to pause here and say, once again, even if we implement all of these techniques that I just talked about in your system and you're like, all of the tests pass, even if a database passes a Jepsen test, it doesn't mean that there aren't any bugs. It just means that we haven't found one. So we have more confidence that our system is doing the correct thing. So visually what this looks like is we've started with our state space, and maybe we're exploring some of it using unit tests. We do some integration tests, and that's going to explore a larger chunk of our state space. And it may overlap with some of the unit tests, so we're doing some duplicate work. Property-based tests will cover another portion of our state space and give us more confidence since we're exploring new areas. And then fault injection testing can cover a different space. But you can sort of see that there are gaps. We haven't covered everything, and so this is where bugs could still lie. But we have more confidence because the probability of us hitting a space that we haven't tested is lower. Another great way to test your systems, and I like thinking of this as testing your DevOps or testing your processes with people, is this idea of a game day. And this is just the operational part of running a distributed system and providing a service is just as critical as writing the code. So game days were proposed by Jesse Robbins at Amazon in the 2000s. He had this title of Master of Disaster, which I thought was pretty cool. And so what he would do is he'd start saying, tell engineers in 3 to 4 months there's going to be a major outage. He would just tell people, like, send out this email. And then people would sort of forget about it, and they'd try and shore up their systems and things like that. And then, someday down the line, they'd actually take out a data center or mimic some really large failure. Like one time he actually mimicked a fire in the data center, and what results in happening is a significant amount of capacity is eliminated from a single data center when they would do this, and so then they would watch and see what would happen to their services. Game days are super critical because they often uncover hidden dependencies. For instance, they ran one where they took out the Sao Paulo data center, and that affected a Mexico instance of an instance of a service running in Mexico. So that was weird. But then they realized there was like a hidden link that they didn't know about. And then they'll find single points of failure. Like I think one they found where they took out a data center, and that was the only one that happened to be running the paging service. So there was like a major outage, and no one got paged, which is bad. So it sort of helps you find this in a controlled environment where the outage is happening, other than like, if you take out, like something bad happened in the data center where all the paging was out and no one got notified, like how long would it take you to figure that out? So if you want to run these in your organization, you can basically notify your engineering teams that a failure is coming. So you're going to do a fault injection test of some magnitude. You will then go and induce the failure. Like this is super critical to like tell people you're doing this because they will super hate you if you don't. You're going to induce the failure, and then you're going to monitor the systems under test. So you basically have like a war room or whatever of people like looking at the systems and being super hawkish because you are testing in production. This has the ability to impact your users, but it's better to kind of do it now than at 4 a.m. when people are asleep. You also should have a team that is that's basically observing the team monitoring the system and the recovery process. Because when an incident happens and like shit hits the fan, and even like something like it's a planned incident, it's still really stressful, and it's really hard to like be objective about how the processes you have in place to recover are working and like all those kind of communications things. So you have another team that isn't involved with bringing the system back up, that's just watching and taking notes and seeing what happened. And then they're going to go file bugs, because it might be that, like, hey, like, we should stand up the paging service in another data center. Or it might be something like, hey, there was an outage here, and these two teams didn't know who was responsible for, like, the service they depended on. There was no way to get in contact with one another. And so that's a breakdown in communication. Or it could just be like, hey, we found a really gnarly bug in one of our distributed services, and we need to go prioritize fixing that right now. A really great example that was sort of low cost, because I like to show the spectrum of fault injection testing in these game days. They don't have to be like you have to have Chaos Monkey and things running. They can be as simple as running kill 9 on a node in your data center. So Stripe ran one. This was back in 2014, but I like this example still because it produced a really interesting result. So they planned to do this, and so they wrote a blog post about it. And basically what they did is they ran kill 9 on their primary node in their Redis cluster, and when it came back up, it lost all of the data in the cluster, which is kind of cool and terrifying. Luckily, they had backed up all the data in case something bad had happened so they could restore and did the responsible thing. But what ended up happening is basically they used some configuration setting that the author of Redis basically said he didn't expect people were going to use it this way. And so it was good that they tested it, because when you start doing performance hacks or like using things that are off the main line, and especially in open source software, it's probably not tested super well. So what actually happened, if you're interested from a distributed systems perspective, is the primary node went down. It hadn't persisted its state to disk because of this config setting they used. They were using something where they were flushing periodically for performance. And then when it came back up, it still thought it was the primary node, even though leader election had happened and there was like another primary running in the system. And so it took the fact that it had no data on its system, and it's like, oh, this is what everyone should have. So it like sent the messages to everyone else in the cluster and said, you all should have no data too. So all the secondary nodes were like, cool, and they deleted all their data. So that's bad. But luckily, they caught it. They didn't have a huge incident where they weren't prepared and didn't have a backup of the data. And so, like, kudos to them for testing this. And it's really just as simple as running kill 9 on a node. You could do this in integration testing where you have 3 nodes running on your machine, maybe in a Docker cluster or whatever, and you just kill one of them and see what happens. This is super, super simple and low cost, and you don't even have to do it in production. So I'm going to segue onto some thoughts on testing in production. I think we talk about testing in production a lot, and it's a little bit cowboy, and it kind of drives me a little bit crazy because it totally works if you have the infrastructure to support it, like Netflix or something like that. If you do not have that large scale of infrastructure, and you don't have a baseline idea of where your reliability and fault tolerance in your systems are, you are essentially testing on your customers, and that is bad. There is always risk about testing in production. So when you run these tests where you say, hey, we're going to kill a node in production, and we haven't done the due diligence maybe of killing it in staging first, because that Stripe bug could have been reproed in staging, we are risking our customers' experience on our product. So that's kind of scary, I think. So there's always this tension. It's obviously more work and more cost to set it up in a staging environment. And you do want to test in production, right? You do want to force your production systems to fail to ensure that the right things are happening, but do some due diligence first and do the proper amount. It's not like the only thing you should be doing. You should be doing some of these other strategies that we talked about. Finally, monitoring isn't testing. People say this to me all the time because I was like the tech lead of observability at Twitter, and they're like, oh, monitoring's testing. And I'm like, not really. All it's doing is telling you what your system that you chose to implement metrics on is currently doing. It's super crucial. You 100% need monitoring to run a system and do operations and effectively run a distributed system and detect errors and respond to things. But like, if you just have monitoring, that is not a form of testing. That's only reactive operations. It just helps you know that something bad is happening. It doesn't prove, or it doesn't give you confidence that anything good is happening. Another one that's like testing in production is canaries. I think this is a super great practice, and you should 100% use this if you can. But once again, it's testing in production, so do your due diligence first to have confidence that that build you're going to roll out is not doing something weird. So the idea of canaries, if you haven't heard of it, is, or it's sometimes called like green-blue builds or things like that. So you're just going to roll out a new build into production on a small number of nodes. Usually you start at 1 and then sort of scale up. If you have really great infrastructure to support this, like maybe it'll just auto-detect something's wrong and roll it back. If you don't, you can have someone like manually watch it and then look at certain key metrics and then make a decision on whether we should increase the canary population in the cluster until it overtakes the whole one. This is nice. And then like if the canary went wrong, you could roll back. This is nice because it gives you some confidence as you're rolling out, maybe even to a really large cluster, that the right thing is happening as you see your metrics sort of not tank and like people aren't having a bad experience. And it also reduces the risk around deployment that you catch something faster, but you still are testing in production. I sort of also like this visual to sort of explain all the different techniques we've just talked about. So there's this idea, and Inez Sombra has a really great talk that's linked to in the references section about how you're building resilient systems. And so this is sort of an idea of how we classify the faults that we find in resilient systems. So there's like the probability of the failure, and sort of the rank of how bad it is when it happens. So if you think of this area under the curve as like all the bugs in the system. So there's a bunch that classical engineering can catch. There's a bunch that you can catch with reactive ops, and then there's this unknown unknown. So this is the thing that like, there are always going to be unknown unknowns in the system. There are too many things to enumerate. And so these are the catastrophic failures that happens where you lose, where you have a really bad outage because no one could think about what had happened, and then you learn from these, right? But these will always be in the system. So I like to think of it like this. If you use unit and integration tests, that's normal classical engineering. If you use property-based testing, we can sort of extend the region of classical engineering because we're exploring more of the state space with sort of a simple technique. Fault injection testing will also extend the space of bugs we can catch with classical engineering. And then you add things like canaries, game days, monitoring, and while this isn't catching things before they go to production, we are catching things in production and having and increasing that space of that we can react to, and we're reducing the unknown unknowns here. And so that's the really critical part, because we just want to keep reducing that space, because those are the things we don't know that are going to happen. Those are the things that are going to take down our system and cause major outages. So this is sort of like a nice handy graph when you're trying to make a selling point of why you should do these different things, is because you significantly get to A, decrease the amount of ops work you have to do, and B, decrease the amount of potentially really bad things that could happen. Okay, so I want to talk a little bit about some research on verifying distributed systems that's ongoing that I think is super cool. I'm only going to talk about one of these just for time, but there's links on all of them in the references section if this sort of tickles your fancy. I want to talk about "'Cause I'm Strong Enough." This is a super cool paper that also came out of POPL 2016. I really liked POPL 2016, if you can tell from this talk. There was a lot of really interesting, I think almost kind of practical research from a programming language conference, because sometimes there isn't, from an industry perspective. And so what this tool that's called Caitie, or "'Cause I'm Strong Enough" did is, the premise is it's really hard for developers to reason about what type of consistency choices you should make in a distributed system, right? Because obviously you want to choose weaker forms of consistency because then you have higher availability. But sometimes you need a really strong form of consistency to enforce a certain invariant. That's like a business decision, right? I must not lose this data, or X has to happen before Y, or finance. There's all these different things. We'll go through a real example. And so what this tool does is it's trying to help users understand and give them a tool to reason about how do you know that you've picked a strong enough consistency model, and how do you only use the minimal amount of consistency, right? When you're designing your application, because you don't need super strong consistency for every operation. You might only need it for one. So what they did with Caitie is there's this example of say we were going to design a bank application, a super simple one, and it's distributed. So the invariant that we must always preserve is that a bank account must always be greater than 0. You want to be able to deposit money into this account, and then you want to be able to withdraw money from this account. And these can happen at any node on the system, right? So Caitie works like this. It's basically, so this is Java, and all of these annotations are Caitie. So what you do is you write your code in Java, or you define your classes, and then you're going to define your invariants using Caitie annotations. So this top part says basically the balance always has to be greater than 0. This is an invariant that must always hold. This second part basically says what are the invariants for the deposit account. So we're basically saying the amount you input must always be greater than 0, so it has to be a positive number, greater than or equal to 0. The balance, what it's going to do is say the balance equals the balance plus the amount. And so then if you just ran Caitie without the debit part, it would be cool, you don't need any kind of strong consistency here, because a positive number added to a 0 or a positive number is always a positive number, or 0. So this doesn't violate our invariant that our balance has to be greater than or equal to 0 at all times. So I can literally add the money at any node without having to do some sort of round of consensus in between. The final bit is on debit, right? So debit's a little different because we have the amount that we added and the balance, and we're still saying the amount has to be greater than or equal to 0, so this is so you don't have to deal with negative numbers. And the balance is now going to be the balance minus the amount. So in order to force the invariant that our balance is always greater than 0, we cannot perform this operation. If you didn't have, there's a token in here, there's basically a consistency token in this correct one, but if you didn't have that in there and you ran Caitie, it would throw an error. So it would basically tell you your design says you have to have strong consistency here because I cannot guarantee that the balance is always greater than 0 unless you talk to all nodes, get consensus on what the balance actually is, and then decide if you can debit the amount. So this is a nice way. So the thing that's cool about Caitie is that it basically is Java annotation that sits on top of your code. It doesn't do anything to help you implement that code, but having the design next to the code makes it easier for developers to reason about, and then you also sort of have docs that live right with your code. So I think it's a little nicer. This is actually open source. You can go play with it. There's not a ton of documentation around it, but the researchers are, I think, fairly interested in hearing from folks, so if you want to try using it, go ahead. So this is just Java JVM. It's really neat. I think this is a really great example of where we should be working towards in the future, where we start writing tools that incorporate ideas from formal verification into design and languages so that they can help us detect when we're running into problems and we're going to make bugs, because it's just a lot to think about. There's just so many different variables going on in your head because that state space of what the possible inputs are is huge. Okay, so in conclusion, if you have something like a really critical component, if you're an infrastructure company, maybe you want to investigate using formal verification on those. Unit tests and integration tests find a multitude of errors and are sort of the baseline. Like, you should 100% have them. I really don't feel like there's an excuse for not having them. And then you can increase your confidence via property testing and fault injection testing in your systems. These yield very, very high rewards, and you can they're on a sliding scale of effort of how much you want to invest into them, because I'm totally realistic about, not everyone can go build a Netflix-like infrastructure. So I'm going to close with a quote from my friend Camille Fournier. Enjoy the ride, have fun, and test your freaking code. Thank you to all of these lovely people who helped me with the talk and the original article. And now we have some time for questions. This is the link to resources, and I'll tweet out the slides and the resources link afterwards as well. Thanks. Yes? Mm-hmm. Yeah, so if I understand your question correctly, you're sort of asking, like, if I'm building the infrastructure and not using it, how do I sort of test that and really increase the confidence that I'm putting out a good system for people to use? So I would recommend going and reading a little bit more of that Simple Testing Can Prevent Critical Failures paper, because there's actually a really ton of great info there. But just to sort of summarize, like, one of the big things I didn't talk about in this, but they talk about it in that paper a lot, is a lot of bugs, like 25% of them come from config changes. And so it's like a place where we don't do a great job of testing our code, and it's also because of, like, the more config options you add, obviously that increases the state space that the system could be running in, and so limiting the amount of configs options to what you can really test. So this becomes, obviously it's once again a balancing act between your customers are asking for this and you want to, like, provide it to them, but then you aren't exactly sure how that interacts with another feature. So being really diligent and having, especially when you're starting to do something like shipping sort of an MVP or a very, very smaller subset, will produce a more correct system. The other thing that I like too is, use a code coverage tool. The result of that paper is they basically make a code coverage tool for Java that you can run. I mean, it's a tool for Java that will run and detect code coverage misses, or it'll just tell you that, like, hey, we found these weird things where you have an error case and you don't do anything. You don't really handle the error, and it'll sort of flag all of those. And they did find a bunch of bugs and stuff and report them to open source communities. But you can enforce this with code review and basically use a code coverage tool, which is might be easier and, like, a little easier to get set up than whatever custom thing they implemented that may or may not work now because it's a research project. And like having... Right. So I'm trying to remember the numbers off the top of my head. They actually, they found a fair number of really, like, good bugs. Like the false positive number was acceptable, basically, because what they did is they ran it on the 5, and then they increased it to like 9 or 10. And so they have more stats on there, but they were basically saying it was worth it. And most of the requests that they submitted to these open source projects were greeted with like, yeah, that's a bug, we should probably fix it. And a lot of them were fixed. Yeah.
What code coverage tools do you actually use?
I mean, it depends on the language, obviously. So I've been running some Go, so like Go has one that's like built in, so I just have it set up and running with Travis CI. I don't like have anything particular. I don't think like there's anything super magic about a code coverage tool other than like it's easy to work with your infrastructure, so it's very company dependent, I think. Like what can you run consistently and give feedback to users and maybe gate check-ins on, or at least expose it during the code review process that like, hey, this is gonna drop code. I'm not a super stickler of like it has to be 90% or whatever. It's more of a tool for you to make a judgment call to say, this is gonna drop coverage, is that okay? Hey, look, all the coverage places that you don't have are error handling cases. So easiest is best, in my opinion. Yes? Do we have fault injection testing at Twitter? So we don't have anything like super, robust as of Netflix, but we do fault injection testing. Like nodes in our data centers die, so it just happens by sort of running the thing. But then also like on the teams I've been a part of, we definitely will test in staging to ensure that if we're implementing a new algorithm that like it can handle that. And that if a node goes down, like the scheduler repicks up the right thing happens, all those kinds of things. So it's more ad hoc, I would say, than at Netflix where it's an infrastructure that automates it for you, but teams do it. Yes? Yeah, so to repeat the question is, like, it's easier to justify fault injection testing in production if it's something that, like, you can gracefully degrade away from, but it's harder to do for something like, yeah, like, killing a zookeeper node is really scary. I don't know, like, many places that, like, do that regularly because it usually results in a lot of outages when it does happen. So it's a risk-reward trade-off, right? Especially if you're gonna implement something custom, do it in staging first, maybe. If it's gonna be something really hard, like where you're gonna, you don't have a ton of extra capacity, so that's a problem. But then, like, if it does happen, like, you're kind of screwed anyway. So it sort of is this, thing where I'd like us to do it more and more because it means we're doing capacity planning more correctly because we have to, like, account for, like, we're gonna fail this much. And fault injection testing doesn't mean I have to survive every fault. It means I say I'm gonna survive these faults. Like, these are the list of faults I'm saying we're gonna survive. Like, it doesn't mean I'm gonna survive multiple, like, maybe, like, for, like, your system, it might not make sense to say we're gonna survive 2 Amazon data centers going down, or whatever, right? Like, that's a business decision about how much money you wanna spend to, like, make your system more reliable, and how many backups and stuff you wanna have. It's the same thing where we replicate data. We replicate in triplicate usually because that's good enough, like the probability of 2 things failing and then like the third one failing before we can replicate it is fine. But like if you really cared about a data, you might replicate it in like sets of 5 and things like that. So I don't have a good answer, I guess, is the cop-out on that question. It's sort of, you have to talk to your business needs. Cool. All right, thank you so much. I'll be around for a little bit if you have questions afterwards.